Hello, welcome back to the second session of the morning. I'm Silvia Zorzetti. I'm from Fermilab. I am a PI and serve as an ecosystem trust leader for the SQMS Center, which is one of the 5 DOE quantum research centers. So I'm here and I'm very pleased to chair the session today. For today, the first speaker is Dr. Altepeter, who is a program manager at DARPA. Dr. Altepeter joined DARPA as a program manager in 2019. His interests include quantum-inspired technology, novel sensors, and imaging systems. Dr. Altepeter is currently focused on evaluating long-term utility of quantum computers. Before joining DARPA as a program manager, Altepeter was associated at Barbarian & Company LLC, and before his consulting work, he was assistant research professor at Northwestern University. He was also an intelligence community postdoctoral fellow, a National Science Foundation graduate research fellow, and a Fulbright scholar. Altepeter received a Bachelor of Science in Physics from Washington University in St. Louis and a PhD in Physics from the University of Illinois at Urbana-Champaign. Please help me welcome Dr. Altepeter.
Hey, good morning. So it's definitely extremely good to be back in Illinois, where, as you just heard, 20 years ago I was getting my PhD at the University of Illinois in distributing photonic entanglement, and 15 years ago I was an assistant research professor at Northwestern working on some of the first telecom band experiments in that space. But for, I would say, the last 15 years or so, I have been working with DARPA and IARPA trying to develop pretty much every quantum computing program that has come out of those two agencies in the past 15 years. And if you haven't heard of them before, they're kind of the mad science divisions of the defense and intelligence communities for the federal government. And what may surprise you to learn is for most of that time, I have been DARPA's designated quantum computing skeptic. So when you were applying to DARPA for quantum computing funding, I was definitely the reviewer you did not want to get, because I measured my success based on how many dumb quantum proposals I could make sure that we did not fund. And if you've been in this field for some time, it will not be difficult to imagine that there were plenty for me to judge my success by. And though I've worked on a lot of things at DARPA and IARPA over the last 15 years, this is kind of what I do now. And I'm going to talk to you about a new national initiative that we're starting that is really entirely focused on separating hype from reality in quantum computing. And so if you are a quantum optimist and you are really excited to show the world that quantum is going to be the most exciting technology of the 21st century, we would love for you to work with us. And if you are a quantum skeptic and you are most excited about proving that none of this works and will never work, we would love for you to work with us, because we need both kinds of people to succeed. So when I think about quantum hype, it's not hard to name, a ton of fields with huge market caps available, or to talk about security and to come up with reasons that sound plausible in the first 2 paragraphs of an archive paper for why this is definitely going to change the world, for sure. But when you dig into these, there's often not a solid case for any individual application for exactly how it's going to work and what it's going to do. And so most of my time in the past 5 years as a program manager at DARPA has really been focused on answering what I feel are the 2 most important questions in this space right now. So the first, which we address with this quantum benchmarking program, is if you had a really big, really great quantum computer, what would you do with it? And why would that, no kidding, be industrially important? And the second is there anybody who is really on the path to develop one of these in the next decade or so? And that's this terribly named US2QC program. And so maybe I'll spend most of my time today, and I was promised that because this was the University of Chicago and there would be PhD students in the audience, I was allowed to use graphs in my presentation. So I hope that's okay. And so when we started, I'll start by talking about the applications, because if there's nothing to do with your quantum computer, we don't need to worry about who's going to be able to build one and who's not going to be able to build one. And so we attacked this problem a little differently than you may have heard. So most of the grants, even from the federal government that I know of, and a lot of the consortia are focused on questions like, what's the most useful thing I can do with quantum computers today? Or what's the most useful thing I can do with quantum computers tomorrow or in 5 years? We tackle this problem by trying to say, let's just go find the experts in the fields that people are hoping to revolutionize with quantum computers and ask them what they would really need to make a revolutionary change in their space. Without ever mentioning quantum or qubit, just imagine you have a black box computer that does something that you need. Tell us what it needs to do and how that would revolutionize material science or quantum chemistry or optimization or finance. Let's calculate how big of a quantum computer you would need to do that thing and see which one of which of those applications hold water and which don't. And so as you can see, we asked a lot of people to help us do this. This was a really big program to basically figure out if it makes sense to have a program in quantum computing. And after 18 months of asking that question, we looked at over 200 classes of application, and we narrowed it down to about 10 that we thought we could get traction on and really answer this question well. For those of you who brought your calculators, you'll notice 10 is quite a bit smaller than 200. That means we found a lot of things that just didn't work, or that we couldn't figure out a way to predict if they would work, which for our purposes was pretty much the same thing. But I wanted to say after that and give you a sense, and here's where I start to use these graphs, of how much DARPA's view of this space has changed over the past 5 years. And so to do that, I want to orient you to this space. So first, there is no two-dimensional plot, which is a good way to visualize what quantum computers can do. They're all terrible. This one, I think, is a little bit less terrible than some. But all you really need to know is the x-axis on this plot is how big of a computer you have. Go to the right, your computer gets bigger. Go up, the computer can work for longer. It has a better error rate. It can do more operations before it all goes to hell. And so a point in this space is one particular computation that you want to try to do. And you can kind of map out the regions of this space, right? There are some spaces to the left and to the bottom which are not going to be useful because you can definitely do all that with classical computers, no problem. And then you come up with kind of two regions, these green and blue regions, where you could plausibly attack the green region with the noisy computers of today or tomorrow. And then there's this blue region where you have to start making your computer, no kidding, resistant to errors. And jumping from that green space to that blue space is like a chasm of engineering difficulty. It is incredibly difficult to do that. And we just wanted to know, of these applications we track, where do they show up? And there's a little red box in the upper right, because I picked a random result in the literature for how big of a quantum computer you need to be able to factor the kinds of RSA keys that protect commerce on the internet, which for a long time was really the only thing we knew about that for sure that you might be able to use a really big quantum computer for. So to recap, points on this space are computations that you can do. Maybe we can guess at where you might have science or industrial applications. And of course, we're going to try to compile these and optimize these so the same computations get smaller and easier to do if we can. And then we're going to compare those computations to actual computers. So the kind of noisy intermediate scale computers, the ones that don't have error correction, those are going to look like a box in this space. They can solve problems inside the box down and to the left. Fault-tolerant quantum computers, for reasons that I won't go into in this space, look more like a staircase, depending on exactly how you configure them. They still handle everything down and to the left. And 5 years ago, we basically had a point. This you could factor large numbers with it. And you can argue about where that is, but I just picked someplace, and it's way up and to the left. Really hard. And I've plotted a few, not all, of recent demonstrations in noisy intermediate scale computers down and to the left with these boxes to give you some sense of scale of how far away we are. And notice this is a log-log plot, so pretty far away. But then, after that first 18 months, after digging into those first 10 applications, we started to get the sense that, well, there are some points on this plot that we haven't been able to disprove. Because I really think of my programs as trying to disprove quantum applications, and the ones that are left standing are the ones that we should really focus the federal government and all of your attention on, because we want to drive towards things that are really, no kidding, going to make the world a better place, instead of the things that are going to generate nature and science papers. And if those are the same, that's great, but in my experience, they're generally not. And so we had a few points, and the thing that started to get us really exciting, and that has been one of the big motivators to start this new quantum benchmarking national initiative, is that 6 months later, we had a lot more points on this space. And it's not important to know like exactly which ones they are. There are a couple things I want to point out, though, which is I'm not sure of any of these points. There is no point on this plot with which I have total confidence. In fact, I'm really hopeful that my team is going to be able to disprove within the next year half of these points. That's my best guess. But I think we've gotten to the point where the things that will cause all of these to fail are decorrelated enough that the preponderance of evidence shows that there are going to be some industrial applications left standing. And that leads us to the conclusion that probably if somebody could build one of these really big, really fault-tolerant quantum computers, it actually could make a difference. So what do we do? That means we really need to know, is somebody going to be able to build a machine that can do this on the scale necessary to make a difference? And here we also take a different approach. Like in applications, we kind of start at the end. Instead of asking what's the best hardware you can build next year, we ask for the problems that are our best guess at really making the world a better place, what's your plan to get there? And so we've started kind of a pilot program in this US2QC that we're now expanding into the Quantum Benchmarking Initiative, a much bigger program. In both cases, we start at the same place, and we ask for your group or your company or anybody who thinks they're going to be able to change the world by building a new kind of quantum computer, we ask, what's the one you really want to build? Forget about proving what you could do in the next few years. Forget about where you're going to get the money to do it. What's the one that you think is really going to be able to make the world a better place? And tell us why. Like, prove to us why that's the one you want to build and why you think it's going to make a difference. And then let's talk about how we follow you along as you develop the components and the subsystems and the prototypes that prove that you can really do that. And if you get through that gauntlet, and we still haven't been able to knock your idea down, because we're going to try to prove that whatever you're doing doesn't work. And we're going to bring dozens and dozens of experts to do it, from national labs, from the government, from private companies, the best people that we can find. And if you make it through that gauntlet, then we can be your advocate in the federal government and say, hey, Department of Energy, hey, Department of Defense, you have this hard problem. We think we've proven that this kind of machine would solve that problem for you, and you should go buy one. And I'm continually amazed at how many people are willing to step into that gauntlet when we're very upfront about, I am going to hire the smartest, best verification and validation teams that I can find in the world to try to prove that your approach doesn't work. And everybody puts up their hand, like, yes, let's do that. We want to go through that gauntlet. And so, just if that led us to the point where a few months ago, right here in Chicago, with Governor Pritzker, we were able to announce a new quantum benchmarking initiative, which is really designed to, instead of tackle this in a small pilot program that looks at just a small number of companies and a small number of applications, to really try to cover the waterfront and see who can do this for real, and who wants to step up and be evaluated. And the details are what I walked through before, which is we want to start with, tell us about your concept in the end. And if that works, we'll try to track out if your R&D plan can really get there. And if that works, we'll really set up an experimental verification and validation system to see if your components and subsystems and prototypes and algorithms and quantum architectures all pass muster, until we get to the point where we could say, yeah, we think if you started construction on the big one tomorrow, it would work, and it would solve a problem that industry or the DOE or the DoD or another customer really cares about, and it would be worth it. Or we show that it doesn't work, and we generate a new roadmap for the next 40 years of basic research and development to get there instead. And so this is the initiative we've launched, and we're moving at record pace. We've gotten in all of the initial applications. I can't talk about how many we've gotten or how good they are or who's going into the next stage, because one of the reasons people work with us is it's a matter of federal law that we can't tell anybody anything about the proprietary information that we get or who's applied until we launch sometime in 2025 with a new batch of companies. But I remain extremely excited about the prospects for this initiative. One of the reasons we're here today, and one of the reasons I am extremely excited about this partnership with Illinois, is everything you heard from Governor Pritzker and from our other speakers and from David earlier today, is that Illinois really is developing a huge partnership. And they're developing a huge campus. And one of the things we're going to need if companies make it into this final stage is a world-class verification and validation facility. And so Chicago isn't the only place that we're talking about working with. We're going to do this wherever it makes sense for whichever company you are. But what Illinois is putting together is extremely impressive, and I think it's going to be attractive to a lot of companies to work here, and we're really thrilled to be able to partner with them. And if it makes sense, then make a pretty big investment here. And we won't really know what makes sense until the data speaks, because we are really very serious about separating the hype from reality. And I get this question all the time. If in 2 years we prove that there's no real path to a useful quantum computer, are we really okay walking away? And they're like, yeah, we just want to find out what's real and what's not. But I will say, as DARPA's designated quantum skeptic, I am more optimistic now than I have been at any point in the past 10 years. And so I'm starting to think that, maybe this could really work. And that optimism and that real commitment to separating hype from reality has led to a major partnership with the Department of Energy. Because the DOE spends a lot of money on supercomputers. They have big computing challenges that they need to solve and that they need to solve today. And we've gotten really enthusiastic support from them in figuring out which path should they be on. Should they be on the path to acquire a really big system within the next 10 years because it's the cheapest, best way to tackle the problems they need to tackle? Or are we on a longer 30 or 40-year timeline? And if so, how should that inform the basic research and development path that they're on? I guess maybe the thing that I'll end on is, instead of talking, which I normally do at this slide, about, well, we can change the world by preventing strategic surprise for national security, or by making real industrial advantage for changing the world. Since there are so many students in the audience that I can see, I guess I would encourage you to try to take up this mission as well and be quantum skeptics. Just because something is written in the first couple of paragraphs of the archive papers of the star student that came in the lab before you doesn't mean that it works. And if your professor or the company you're working with is telling you this application is fantastic, if it sounds fishy, if it smells fishy to you and you can't figure it out, you should push back and try to figure it out, because there's hundreds of potential applications out there. And whether or not this community that it's so exciting to see Illinois building works is really going to depend on your ability to pick the subset of applications which are really going to change the world versus the ones that sound good today. And to the professors out there who now have a newly invigorated and argumentative batch of graduate students, you're welcome. And so I think I can take questions.
An outcome of this program could be that to build a utility-scale quantum computer would take like a mega project level of investment, where like International Space Station or like Large Hadron Collider type investment that no single company can do. What would DARPA's reaction to that be?
I think there are so many decisions that have to be made around how to invest from the federal government's perspective, and not just what's the smartest thing to do in quantum, but should we be doing this or should we be trying to cure cancer with the money instead? All of that gets better with better data. The most important thing is to get the answer about what it would take to build a system that's really utility scale and what it would do that would make it worth it. And if you solve that problem first, then those questions get a lot easier. because then you have a good idea of what it's worth and how it will change the world and what it'll take to build it. And one of those is bigger than the other. And then it's a lot easier to make that decision. And before you have that information, it's really difficult to make strategic investments because you don't know what you're making them towards. And there's so many different flavors of really exciting quantum computing out there. They take totally different infrastructure bets. They take totally different basic research and development bets. And at DARPA, we are making a bet that a clearer vision of the utility of quantum computing of all types will make us smarter about these hard decisions.
Is this program focusing solely on platforms being built by companies, or even beyond that? I mean, we know that there is a lot of research efforts to do hardware development at universities, at national labs, various type of national labs. So who does the benchmarking of what's being developed in companies versus not in companies?
Yeah, that's a great question. So I think really it's two questions. It's who do we want to fund to follow along and see who's on the path to build a utility scale quantum computer and for what purpose? That, my guess is mostly going to be companies, because most of the companies in this space have a different level of investment and a different speed with which they're working than smaller academic groups who are solving important research problems but not trying to build a quantum data center in the next 10 years. The other half of your question is who are we going to get to help us understand which things work and which don't. We have already assembled what I am reasonably sure is the largest and best verification and validation team for quantum computing in the world. And we know that we have to make that a lot bigger. And so we just got through an RFI process, basically asking absolutely anyone, state governments, universities, companies, national labs, other government agencies, anybody who thinks that they would be good at this and want to work with us to put in their responses. And we got an incredible response. We got a huge number of responses. And so right now we have the exhilarating task of trying to figure out how we build an even bigger, best quantum computing verification and validation team in the world. And I just don't know the answer to how that's going to shake out in the end, but it's extremely exciting to be a part of that process.
I absolutely enjoyed your talk and the way you thought through the program. My question is, how do you engage with other government agencies? Do you have a program with other government agencies and executives can come to you and you guide them? This is how you actually think through quantum. It's not a done deal where it's going to have like a massive economic impact that's up in the air, but you should still invest, and here's why. I think the money that you probably invest, there's probably 2 or 3 orders of magnitude that combined everything else gets invested. It might be worth having such a program.
Yeah, I mean, I guess the answer is that we aggressively and are constantly are engaging with other government agencies in the quantum space. What we found is that people are really extremely eager in the federal government to have this sort of rigorous evaluation of which applications really have a chance of working and which hardware paths really have a chance of working. And so those lines of communication are really wide open. And a huge percentage of my time is spent briefing other people in the federal government on what we've learned and learning from them which types of computer would really be the most useful to them to make sure we can do our job right. Thank you.